Since starting this YouTube channel, I've made 17 maps on different areas of physics. And one thing I've learned is that physics itself is still incomplete. This is really annoying because I want to understand things about the universe, and there's many big mysteries that we just don't understand. So this makes me wonder, will we ever be able to complete physics and have a complete understanding of the universe? Or is it actually impossible? In this video, I'm going to look at some of the biggest mysteries that plague physics today and try and gauge whether those will be one day solvable or whether they'll be forever outside of our reach and we just have to give up on any hope that we'll actually ever understand everything about the universe. So I was thinking about what you need for a successful theory of physics, and essentially there's 8 things you need to describe. So first you need a description of space, so 3D space, and then time, then matter, the stuff in that space, which is mostly atoms, and then you need to describe energy, which is basically how anything happens. So if you describe how energy moves through matter in space and time, that's basically all of what physics does. Okay, so that's the first 4. Now the second 4, we've got the 4 mechanisms of how energy can flow around, and these are the 4 fundamental forces. First, gravity, the old apple on the head. Basically all matter in the universe weakly attracts all other matter. Then electromagnetism, this is basically everything else that's not gravity. If you zoom in on any process closely enough, it's governed by what the electrons around atoms are doing. Mechanical processes, chemical process, how light works, electronics, that's all electromagnetism. And finally, the nuclear strong and nuclear weak forces, which happen inside the nuclei of atoms. And these are important in nuclear physics and radioactivity, but we don't experience these day to day. So these are the 8 things that physics needs to explain, and today we can't explain all 8 with one single theory. Okay, so the biggest problem in modern physics is that we don't have a theory of quantum gravity. To explain what this means, we need to look at my map of physics for an overview. This was actually my first map I made on this channel. If you're new here, I've made loads of maps about various subjects, and if you want to get your hands on any of these, I sell them as posters. The links are at dosmaps.com. I'm about to go on paternity leave. I'm having my first child. So if any of my work has been useful to you and you want to help me out, this is a great way to do that along with my Patreon. So all of the links to all of that are in the description below. Thank you. But anyway, the map of physics. Physics basically boils down into 3 sections. We've got classical physics, relativity, and quantum mechanics. Of the 8 things that physics needs to describe, classical physics covers these 6, but it doesn't really describe atoms. So we need quantum physics for the strong and the weak forces. But classical physics is really just an approximation for human scale. So the correct description for time and space is relativity, where it's split into 2 parts. Special relativity puts space and time together into a combined entity called space-time, and then general relativity describes gravity as the curvature of that space-time. Then at the bottom we've got quantum mechanics, and that's the accurate description of electromagnetism, matter and energy. So all we need to do is join quantum mechanics and relativity together, and then we'd have a theory of everything, a theory of quantum gravity. Now, people have been trying to do this and have managed to jam quantum mechanics and special relativity together into a theory called quantum field theory. But whenever anyone has tried putting general relativity and its description of gravity into quantum field theory, it doesn't work. There's a fundamental incompatibility with the smooth, continuous nature of space-time and the blocky, chunky nature of quantum mechanics. And if you smash all the maths together, you end up getting infinities and paradoxes, and it doesn't work. People have been trying to do this for over 100 years unsuccessfully. So for now, a theory of quantum gravity is on the other side of the chasm of ignorance, along with other big mysteries like dark matter and dark energy. Dark matter is basically some form of unknown matter that makes up 85% of the universe. We know what makes up the normal matter, that's described by the standard model of particle physics, but this is only 15% of the universe. We probably won't need a theory of quantum gravity to explain dark matter. People think it's just another kind of particle that only interacts via gravity and not the other forces, but we're still figuring that out. Dark energy is quite different. Dark energy might be another kind of force that we'd have to add to these 4. Basically, at the large scale, the universe is expanding. But not just expanding, the expansion keeps speeding up, accelerating over time. So there must be some force or energy pushing everything outwards. We don't know what this is, so we called it dark energy. It seems like space itself has some inherent energy, which could perhaps be explained by theory of quantum gravity, but we don't know that for sure yet. I've made a deeper dive video all about quantum gravity. If you want to find out more, watch that. But for this video, what I really want to know is if we'll ever be able to get to a theory of quantum gravity at all. Because we need it to explain two of the big mysteries in physics: black holes and the Big Bang, the origin of the universe. This is my map of black holes, and basically we don't understand what's going on inside them. Black holes are such an extreme environment in the universe that gravity and quantum mechanics simply can't ignore each other. So to understand black holes, we need to have that theory of quantum gravity. And for similar reasons, for the Big Bang at the start of the universe, as we know, which is like 13.8 billion years ago, the whole universe, according to our best models, was squidged into a tiny subatomic volume. So we need to have a theory of quantum gravity for that original form of the universe as well. And here's a crazy thing about the Big Bang. As the universe expanded, there's a point here where the matter was spread out enough for light to escape. And we can see that first light today as radio waves. It's this, the cosmic microwave background. And this is the furthest away thing we can ever see with light. This is the entire night sky, so this covers every direction. And these grains of colour you can see, this is the granularity of quantum mechanics, frozen in time from when the universe was tiny, and now has been stretched out to the size of the observable universe. So the smallest things in the universe now are stretched over the biggest things in the universe. So here's the situation we're in. Our theories of quantum gravity don't work. Our best attempts, like string theory and loop quantum gravity, they don't give us any testable predictions. And this is how science is supposed to work. If you've got a new theory, you need to be able to test it with a prediction. And we don't have any from those theories. The other way you can go about it is that if you've got no theories that are working, you need some new data, something that can give you a new clue about what's going on. So, what experiments could we do for quantum gravity? So, the first option is a giant particle accelerator, like the one at CERN, but way bigger. And you build this to find out if there's a quantum particle for gravity. So, people have hypothesized this particle. It's called a graviton. And to get enough energy, you'd need to build a particle accelerator the size of our solar system with detectors the size of Jupiter. And as soon as you ran it, you'd create a black hole. So, that's not practically going to build anytime soon. Another route you could take is to try and delve down into the quantum realm and make incredibly sensitive measurements of gravity. So there's gravity everywhere, so there should be gravitons everywhere, but they're incredibly difficult to detect because gravity is such a weak force. So one idea is to get a massive chunk of metal, about 1 ton, and cool it down really cold to get rid of all the vibrational energy inside it, and then wait until a graviton bumps into it to make it vibrate a teeny bit. So you'd need a ton of metal, cooled close to absolute zero, and practically this is easier than that solar system sized particle accelerator, but this is still way beyond what we can do today, and it might be physically impossible to protect this detector from other sources of vibrations like cosmic rays or neutrinos, which might hide the gravitons. Also, both of these approaches assume that a particle of gravity exists. That's a very quantum way of looking at gravity, but we don't know gravity works like that. It might work in a different way and not have particles. So currently, with no experiments we can run, our best option are observations of space, specifically of gravitational waves. Gravitational waves are ripples in space-time. These were predicted by the laws of general relativity and then first discovered in 2017. These gravitational waves could be the best chance we currently have to get some clue to point us towards a theory of quantum gravity. We can currently detect gravitational waves from Earth of black hole collisions, and there's a plan to make a much larger space-based detector called LISA. LISA's planned to launch in the mid-2030s, although this date keeps getting pushed back. And I've basically been following the mission since the 1990s. But if this does launch within my lifetime, it should be able to detect primordial gravitational waves from the Big Bang. These primordial gravitational waves come from fractions of a second after the Big Bang, and these are the earliest signals we could get from the origins of the universe, way before the cosmic microwave background, which is the earliest we can currently see. There might also be faint signals of these primordial gravitational waves in the cosmic microwave background itself. These are called B-mode polarization patterns, and this is the quickest route to try and see them. There's loads of telescopes trying to measure this currently. So to understand the universe, we need to have a theory of quantum gravity, and these are our best options to try and find one. So it looks like it might take a while. But here's the kicker. Even if we did have a theory of quantum gravity right now, there's still things about the universe that we know we'll never know. For example, inside black holes, we'll never know what's going on inside them. We can only ever guess, because anything that goes into a black hole never comes out. So no information can ever escape from the insides of a black hole. So we'll never know what's going on inside them. Similarly, we'll never know what happened at the very, very early universe, the origins of the Big Bang, what caused it, anything like that, because there's no information in the universe that could tell us. Similarly, beyond the observable universe, so we can see a patch of the universe, which is 48 billion light years in radius. Beyond that, we don't know what's happening there. Physics could be different, or it could be full of antimatter or whatever. We'll never know. So unfortunately, the conclusion of this video is we will never fully understand the universe. And so as a physicist, that's a bit sad, because our knowledge could never be complete. But isn't it incredible that we can even ask these questions? We're like this little corner of the universe that's been evolved and arranged in this way, where we can actually look out and question why everything is the way it is, and then perform experiments and do observations to try and figure out these theories. It's like the Earth is a floating museum of the possibilities of the laws of nature, and I think that's incredibly precious. I've recently been thinking about the uniqueness of life on Earth and how sad it is when a plant or animal or fungi species goes extinct, because these are unique configurations of the universe that, if they die, they'll never exist again. And this is why recently, with everything else that's been going on in the world, I've wanting to do something proactive and positive to help out against biodiversity loss. So I've recently joined a community of people who've come together to help protect environments and species by pooling their resources together. It's called Planet Wild, and I've actually partnered with them for this video. As an individual, it's often easy to feel a bit helpless when thinking about what we can do to help the environment. But through Planet Wild, over 20,000 members come together to pool resources to fund a new, carefully selected mission each month to bring back endangered species, protect our oceans, restore forests, and many, many more projects, which you can find on the Planet Wild app. You can see all of the projects that have been funded to date, things from saving pangolins from illegal trafficking through to protecting the world's fungi. And what I really like about this is all of the traceability. All of the missions are documented. They're all right here on YouTube, on the Planet Wild YouTube channel. So I can go there and I can see what my contributions have achieved every month. And another thing I really like is they show exactly who they're working with on the ground and specifically what the funding has accomplished. You can sign up for a monthly membership for any amount, big or small. Literally every little bit helps. And also the first 100 people to sign up using my code DOMAIN4 will get their first month paid for by me. Just scan this QR code or click on the link in the description below. After that, there's no catch. You can cancel anytime. Personally, I'm finding it very valuable to feel like I'm contributing, at least in some small way, to push the world in a more positive direction. So if this sounds interesting and you'd like to find out more, please check out Planet Wild through these links. And also, if you want to see their work on fungi preservation, check out their video here. And if you want to see why I think fungi are so cool, I've got a really good overview here. All right, that's it from me. Thank you so much for watching, and I will see you on the next video.